Well, thank you so very much. Tony, it's a real pleasure to be here. And I think I came in 1982. I think that was the same year that you came. You came in 83. Okay, so I beat you here. But so you weren't the reason I came. But there were many reasons to come to Illinois, and being a graduate student here was just really fantastic. And working with you and working with Eduardo, and I was thinking of superlatives, Tony, that I could use to describe you. And I thought of I can think of many of them, but I want to tell a little story on each one. So friendliness. You would invite the group over to your house fairly often. For really nice dinners, and this was wonderful. And as we came in the door, you offered us a big jar of Reese's peanut butter cups. This is coming from an Englishman, and that was nice, but they were the small Reese's peanut butter cups. And as you told us, they were better because there was a larger surface to volume ratio. We all know how modest you are, Tony, and at that stage, preprints, when they came in, were sometimes written, from Russia. They were actually written in Russian. And so Alan Dorsey and Alan was another grad student there at that time. I remember sitting in your office, Tony, and a new preprint had come in, and you handed it to us, and it was written in Russian. And you say, I presume you speak Russian. And I'm like, we barely speak English, Tony. But you're so modest, and it was said with such modesty that we didn't take it personally, but we still don't know any Russian. But fortunately, it was soon after that the Russians started, writing the papers in English. And then finally, of course, everybody knows how deep you are in physics. And the Schrodinger's cat was something that, bothered you enormously then. I assume it bothers you now still, and it's bothered me for the last 40 years. I think many physicists are not bothered by it, but I think I share that with you, and it's a real pleasure to have this institute named in your honor. So congratulations to Tony and also to UIUC in bringing together such a wonderful center over the last 10 years. So what I want to talk about in time here is quantum entanglement, and in particular, taming quantum entanglement. So we learned in statistical mechanics that the second law of thermodynamics says that entropy always increases. Disorder increases as you look at a system, no matter what you do, entropy increases. Now, what about in quantum systems or isolated quantum systems? Well, entanglement entropy is a good stand-in for entropy. And basically, entanglement entropy also tends to grow whenever you have a quantum mechanical system that's evolving in time. So, in physics, we basically learn that disorder always reigns. At long times, one should go into a state with maximal entropy. There should be no structure. But that's not the way the world is. The world is not that way at all. I mean, we're biological organisms here, and we're not entirely random, at least some of us.
Disorder reigns in the world.
What's that?
Disorder reigns in the world.
Disorder reigns in the world. I'm afraid that's true. But in this room, we're very orderly. So I've been interested in how to control the entanglement entropy growth. And I'm going to just mention three different ways to think about this. One is many-body localization. The other is what are called quantum disentangled states, where heavy particles are localizing light particles. And the other is the act of making measurements, where you have a reduction in entanglement. So if you take a simple Hamiltonian like the transverse field or longitudinal and transverse field one-dimensional quantumizing model, start it with a direct product state and just evolve the Hamiltonian, you find that the entanglement grows rapidly, it grows ballistically, and at long times, essentially everything is entangled with everything else. So the entanglement entropy becomes very large. You can do the same thing without energy conservation by running a quantum circuit with unitary dynamics. And you start with an unentangled initial state, and entanglement grows ballistically with time. disorder range. And at long times, you basically evolve into a quantum state, which is completely random. And that's the disorder reigning again. So how to control entanglement? Well, many-body localization is something that's, was a remarkable phenomenon, been around for, conceptually for 20 years. And it's basically when you take isolated interacting particles in a random potential, and you then get a lack of thermalization. Entropy doesn't grow linearly with time if you start with a low entropy state. In fact, in the many-body localized stage, you get very, very slow spreading of entropy. The random potential basically, almost completely stops the growth of randomness. And now, so this is one way to sort of tame quantum entanglement growth. But the random potential constitutes a classical or frozen set of degrees of freedom. And one thing we know, or we believe, is that the entire world is made of quantum mechanical degrees of freedom. And so a question that I thought about with Tarun Grover some 7 or 8 years ago is, can one have a similar type of localization in a quantum-only system? That is, a system in which all the constituents are described quantum mechanically. And in particular, we were focusing on having heavy, almost classical particles interacting strongly with light, very quantum mechanical particles. And the system one can have in mind for this is a neutral atoms made of heavy nuclei and light electrons. And if you take an atomic liquid or a molecular liquid, I guess, when it's cold, 100 Kelvin or so, all of the electrons are bound to the nuclei. But if you raise it to 3 orders of magnitude to 10 to the 5th or 10 to the 6th Kelvin, you're going to start getting an ionized plasma. And a question you can ask is, are the two states, the eigenstates, if you have the isolated system in a box, the same for an atomic liquid as they are for an ionized plasma? And I think the conventional wisdom is they are, because the atoms are always weakly ionized. Even if you have an atomic liquid at low temperatures, there's always going to be some probability that you have ionization. But how do you even define ionization when you're a dense liquid? And so we were thinking about ways to define ionization, and maybe to try to distinguish a non-ionized from an ionized system. We thought of something we call quantum disentangled states, which is a novel class of non-thermal quantum states. And we introduced a wave function diagnostic for that. So basically, what we were thinking is that one has this atomic system described by some wave function which depends on both the position of the atoms and the position of the electrons, big R and little r. We have some finite energy density wave function, which itself is very entangled. It has a high entanglement entropy, so-called volume law entanglement entropy. But now what we want to do is we want to, and motivated by many-body localization, we want to measure the positions of the heavy nuclei and freeze them in place. But we're going to leave the light electrons unmeasured and define an unmeasured wave function conditioned on the measured locations of the nuclei. And then we take this electron wave function and we bipartition, and we look at the entanglement entropy of the electron wave function. And so we look at the entanglement entropy of the light degrees of freedom conditioned on having measured the almost classical or heavy degrees of freedom. And we defined a quantum disentangled liquid as one in which the entanglement entropy of the light degrees of freedom after you measure the heavy degrees of freedom is area law rather than volume law. So in this case, measuring the nuclear position has disentangled, or in some sense localized, the electrons. I mean, the way we were thinking about it is that the electrons are basically constrained to move. Their motion is strongly constrained by the motion of the nuclei. Now, if one actually had, so if one had a quantum disentangled liquid, one would not have any ionization. If one has ionization, then even if you measure the position of the nuclei, the electrons will be themselves in a thermal state, and one will have a thermal wave function rather than a quantum disentangled wave function. Now, this is all fine and well, just ideas. You can ask, do quantum disentangled states exist as eigenstates of generic Hamiltonians? And so we address this by looking at the one-dimensional fermionic Hubbard model at half filling with positive U. So this is the standard model people look at. And we turned on a nearest neighbor repulsion V, so it's no longer integrable, and so it's a more of a generic model. We then, exact diagonalization on small systems, computed all of the many-body eigenstates psi. We measured the spin on each site by making basically a projective measurement. And let's say here are the sites, and if you find spin 1/2, you know there's an upspin electron on that site. If you find spin -1/2, you know there's a downspin electron on that site. But if you find spin 0, there could either be 2 electrons in a singlet or no electrons on that site. And so after measuring the spin, you have the charge degrees of freedom, these doublons, if you will, which are still in some wave function. And you can ask about what's the entanglement entropy of the doublon wave function after you've measured the spin. And I should say that the spins are almost classical because we're thinking in the case where U is pretty large. And so the charge fluctuations are more rapid. So we looked at then the entanglement entropy of the charge wave function post-spin measurement, and a thermal eigenstate would have volume law for the charge wave function, the entropy of the charge wave function after measuring the spin, whereas a quantum disentangled eigenstate would be area law. Oopsie. So here's just some brief numerics on the one-dimensional Hubbard chain. As I say, we computed all the eigenstates with exact diagonalization. What's plotted here is the mean double occupancy evaluated in the eigenstates. Here's the energy density through the entire many-body band. And one has these states here. Now, down here, one has a set of states which are basically almost states like the Heisenberg antiferromagnet. In fact, here's the Heisenberg antiferromagnet and the Heisenberg ferromagnet. The Heisenberg antiferromagnet is the ground state, but this is really in the Hubbard model. And so what it's looking like, although it's a little hard to tell because one obviously can't go to the thermodynamic limit, is that one has a charge band, but moreover, one has what we call a spin band. And here there in this band, there are essentially 2 to the L spin states. And so, if this really survives the thermodynamic limit, it would actually be a breakdown of the eigenstate thermalization hypothesis, because at a given energy, there would be 2 sectors which have different local properties, like the doublon occupancy. So you can also look at the entanglement entropy of each of the states. And what we are finding is in that spin band, the entanglement entropy goes up and starts coming down again. Whereas in the charge band, the entanglement entropy just increases and then comes down at much higher energy density. So it looks like, at least on sizes up to 14, that one has a spin band which is low entropy but high temperature, and a charge band which is high entropy, low temperature, which are coexisting. Now, you can then ask, well, what is the nature of these wave functions in this spin band relative to the charge band? And so to look at that and look at this quantum disentangled liquid diagnostic, we focus on 3 eigenstates. An eigenstate and the high entropy state in the charge band, the highest entropy state we have, a high entropy state in the spin band, it's a little harder to see the spin band, and then the ground state, which has the lowest entanglement entropy. And we basically look at these 3 states. We look at the entropy as a function of the region X that we call the region A of size X, and we look at S of X as a function of X. And in this first vertical column is the full entropy. So here's the ground state and the entropy is pretty flat in here, and that's the area law of the ground state, although it's a logarithm, presumably. The high entropy state from the charge band, one has the entanglement entropy grows, and one has this inverted V, which is a signature of volume law. And the high entropy state from the spin band is also, it looks to be volume law as well. But now we take these eigenstates and we measure the spin, and we look at the entanglement entropy of the unmeasured charge degrees of freedom. And in the ground state, we still have an area law. For the high entropy state from the charge band, so this is the state up here, one has, even after measuring the spin, the charge is, essentially in a volume law. So the charge and spin have independently thermalized. But the high entropy state from the spin band, while it was a volume law before measuring the spin, the full wave function was volume law. After measuring the spin, the charge is an area law. So it looks like that there's a possible, the spin band has these quantum disentangled states where there's an area law for the charge entropy post spin measurement. So, this is the second way in which one can imagine taming quantum entanglement, is to have very heavy particles, almost classical, which are essentially constraining the motion of light, very quantum mechanical particles. And I just had some experimental data. I don't know if this really necessarily has something to do with what I've been talking about, but it might well. But it's interesting in any case. You can ask, what's the electrical conductivity of water? Salt water, it conducts fairly well. Tap water, depends which country you're in, how well it taps. Purified water, where you take out all the salts, is not a good conductor at all, 10 to the minus 7 Siemens per centimeter. But if you take water and you put it under very high pressure, shocked here, that the electrical conductivity rises by like 9 or 7 orders of magnitude, very, very rapidly. I think the way to think about here is that basically the protons have basically, come off the oxygens, and the protons and oxygen ions are contributing to the conduction. Whereas for pure water at standard temperature and pressure, I want it to be in a disentangled states where the protons are locked to or bound to the oxygens in the water molecules. How much time for a few minutes? 5. Okay. Yeah, that's plenty. Okay. All right. The third way that I've been thinking about trying to tame entanglement is with making measurements. And this comes in, to some extent similar to the kinds of things that Tony was thinking about, where you have, as all of this talk, where you have microscopic degrees of freedom interacting with macroscopic degrees of freedom. So we've been looking at what do we call hybrid quantum circuits, which consist of qubits evolving unitarily, which induces the growth of entanglement. But then if you make a measurement, it tends to disentangle. So Tony, if you and I share a singlet, we each have a spin and a half, we have an entanglement between our respective spin and halves, or log2 entanglement entropy. But if you measure the spin of your spin and a half and find it up, then mine will be down and will be in a direct product state after that, and there'll be no entanglement at all. So making local measurements tends to disentangle from everything else. And now the question is, what is a measurement? But as theorists, we just make a projective measurement, and there's no problem. Experimentally, we know how to make a measurement. We just don't understand the connection between the two. So the entanglement transition in these, there's a competition between unitary evolution measurements, and there's this interesting entanglement transition in the monotone dynamics where P is the rate of making measurements. If you make many measurements, the measurements dominate and you get a disentangle phase. And if you make few measurements, the unitary evolution dominates and you get an entangled phase. And so you get this measurement-induced phase transition separating a phase which is, essentially thermal, where the entanglement entropy grows linearly in time, from a phase where you're making so many measurements that you suppress the growth of entanglement. Basically, you just keep looking at the system a lot, and so it doesn't have time to entangle. And then there's the phase transition in between where the entanglement entropy goes logarithmically. So we were thinking, even at the time when we were thinking about this, is the disentangle phase one of these quantum disentangled liquids? So what we decided to do, and to think about this a bit more like the quantum information theorists do, which is when they have a measurement, what they think about, and this is actually true in quantum simulators as well, is they take ancillas, and they take an ancilla, which is another qubit, and when they, quote, make a measurement, they perform a gate, a C0 gate, from the qubit in the system to the ancilla qubit. So they entangle the system qubit, the quantum qubits, the light quantum particles, with these heavy ancillas, if you will. And so if the qubit here is in a linear combination of up and down, then it gets entangled into some sort of cat state between the ancilla and the system qubit. And as we evolve in time, typically one just lets these ancillas have no evolution, and we continue to evolve the system and introduce an ancilla every time we make a measurement. And thinking in terms of quantum trajectories, basically these ancillas encode all of the quantum trajectories in the physical system. And at the end of the day, if we want to actually make a measurement of the system, one has to measure one of the ancillas, or measure all the ancillas. So one is sort of, pushing the subtlety of measurements to later on. So basically, with the Schrodinger's cat, here's the microscopic particle entangling with Schrodinger's cat, and maybe the cat is in a linear combination of alive and dead, but then we open the box and look at the cat. That's the final measurement, and the cat is either alive or dead. So we've been introducing, we introduced recent work with Chengji Sang, a system, or like we have here, chain of qubits, where we're trying to measure, model the measurement devices by degrees of freedom which are almost classical. What do I mean by that? So in each of these purple circles, we have maybe 10 qubits, and we then unitarily evolve the system qubits with some random unitaries. And so that very much entangles the qubits. We evolve the measurement device, because the measurement device has to be treated quantum mechanically. You can't treat the measurement device classically. So we evolve it unitarily, but we take a unitary which is mapping a computational basis state to a computational basis state. So it doesn't lead to any entanglement per se, the classical device. And then with some probability P, we perform C0 gates, coupling the quantum system to these these measurement devices, if you will. And then at the end, what we're going to do, well, we're going to then look at the entanglement entropy and ask what happened with the entanglement entropy. And then we're going to measure all of the measuring devices themselves. That's like opening the box and looking at the Schrodinger's cat and asking what the entropy looks like at that stage. So here we can look at the entanglement entropy growth. This is purely unitary dynamics, right? So whenever you have unitary dynamics, the entropy grows essentially ballistically. And here it's saturating at long times with a value which is set by the system length. That's the maximum entropy you can get. So basically, even though these were almost classical degrees of freedom, the entropy, the state that finally exists at long times, looks like a random state, which is entangling the system qubits with the degrees of freedom in the measuring device, or devices, as we have here. And then finally, we come in and open the box to look at the cat, and that is we're going to make a measurement of these measuring devices. and ask what is the entanglement entropy of the entanglement entropy of the system qubits post measurement of the measuring device. So here we've come in and made a measurement, and after we make the measurement, we end up with a pure state which lives on the system qubits, and one can look at the entanglement growth of those system qubits after making measurements at subsequent times. And if we had a lot of C0 gates coupling, if we had strong coupling between the system qubits and these measuring devices, what one finds is that one goes into this area law phase where the entanglement entropy of the unmeasured system qubits is not very large. It's been, the entanglement has not spread very much, basically because these measuring devices have been essentially making delayed projective measurements on the heavy degrees of freedom. So, yeah, so what I talked about are basically three different ways that one can think about trying to put some order into a world which is disordered. Because the world, even globally, it's disordered, locally it isn't. So many-body localization, quantum disentangled states we talked about, and this quantum entanglement transition where the area law phase in the quantum entanglement transition is, in some ways, it can be viewed as a quantum disentangled state. And you know, the real challenge here, and I think it's a challenge which has been around for many years in physics, is to have general methods to explore quantum dynamics when one has light quantum mechanical degrees of freedom, which are strongly interacting with almost classical heavy particles. So like we learned about the Born-Oppenheimer approximation, where we basically freeze the position of the ions and then solve the electron problem. And the electrons bind to those ions, and so they get localized on those ions. And then we say, okay, now we have the neutral atoms, and we let the atoms move around in the potential that was created by binding the electrons. That state that we consider when we do that is a quantum disentangled state. But that's within the Born-Oppenheimer approximation. Maybe it's a good approximation when the mass is large, but maybe it only becomes exact when the mass goes to infinity, where the nuclei just simply stop moving. And then it becomes more like the many-body localization problem. So I think, you know, when one is thinking about interfacing the classical world with the quantum world, one has to just treat the classical world as almost classical, but a bit quantum mechanical, and try to do, you know, a better job, as I think we're already better job than we can do at this stage, of modeling the quantum measurement apparatus. And maybe, you know, at some point we'll get some insight into, you know, the Schrödinger cat paradox, which is still so worrisome to some of us in this room. So, so Tony, what I want to suggest is that rather than the Sir Anthony J. Leggett Center for Condensed Matter Theory, we just call it Tony's Center. So congratulations to Tony, and also to all the other faculty in at UIUC for putting together such a great center. Thank you.
Okay, we have time for the questions.
Yeah.
I have a question about your second method for taking this entanglement states. So I guess you're trying to do something like MBL without disorder.
Yeah.
With any system that's, you know, low energy is described by some Gaussian theory, like lump for liquid or collision bits are available of having, you know, because there you probably have to, the first two states, you'll have to go higher in the spectrum to see really improvement in volume law. Like, is this something that?
Well, no, but here we're looking at finite energy density states. I mean, these states in what I'm calling the spin band, which seem to be quantum disentangled, these states are, you know, it can be thought sort of morally as all the states, the 2 to the L states in the Heisenberg model. So we're not looking at low energies. We're looking at
Fraction is
the fraction of those states. Yeah, so there's 2 to the L spin band states, and the overall number of states is 4 to the L. I mean, the symmetries which reduce that, to this actual spectrum that we're looking at. I mean, you can label the total spin and total charge.
Andre first.
I think that there's another mechanism for or is this just like another example?
No, I think it's another mechanism. I mean, what's different from Hilbert space fragmentation? What's different is we did this first. No, I'm just kidding. So what's different between Hilbert space fragmentation? I mean, ultimately, the majority of the states in the Hilbert space, if you just pick a state randomly in Hilbert space, is a random state. And so in order to break ETH, you have to somehow have restrictions which put you into some sectors of the Hilbert space. And so here we're saying that a state which looks random, because it's got von Neumann entanglement entropy, actually isn't, because unbeknownst to us, the heavy particles are enslaving the light particles. And so when we measure heavy particles, we see the light particles which are enslaved by the heavy particles. So I think, yeah, maybe similar, but yeah.
Yeah, just a comment. Put this model with the ancillars.
Yeah.
That looks. No, yeah, or this one. This looks reminiscent of what people in EMRG do when they want to simulate finite temperature. The way they do it is they put essentially a set of ancillars which are entangled with the system, and they only look at the system and not on the ancillars or vice versa. So in a sense, that's how I understand they do finite temperature.
Yeah, and maybe there's something like that. I mean, here, here we just, before we make measurements, it's pure unitary evolution. So there is no temperature, energy is not conserved, and it actually will become hot, very hot. And then when you make the measurements, when you measure the ancillas, you can cool off the unmeasured degrees of freedom, which then go into an area law and look cold. But so I'm not, it may have some similarities to that.
I mean, that's what I understand. So, I mean, I'm not an expert, but that's how I understand.
Yeah.
They do. They're looking at ground states typically, and then low energy states at finite temperature. And the way that we
entangling with ancillas and then integrating them out.
Not looking at their value.
But not measuring. I mean, there's a real difference between measuring and there's a real difference between making a measurement and pulling out information, or integrating out and throwing away information. I mean, and those are,
that's what they
they're maybe doing the latter, I think.
All right, so we had Steve and Jung on. Other last questions. Yes, Steve.
Yeah, we're just wondering why you're not thinking about Devon's like phonons, which are the freedom, billions of variables.
Yeah, no, I think it would be good to think about that, metals at very high temperatures where the atoms, are heavy and maybe look, distorted, their positions are random enough.
Well,
Exactly. Yeah, no, I think one can look there. And the question is, what would be the manifestations of this type of physics? And I'll leave that to you, Steve.
Last question.
So you can apply with probability, right?
We applied with probability P the C naught gates.
Then wouldn't it be just that relating classicality of the original set of just like a random applications of UGC, so still things are kind of classical in this sense. But you apply UGC with probably P randomly, right?
Yeah, we're applying. Yeah, I mean, in some sense, this is just the measurement-induced phase transition in disguise, right? I mean, but we're treating the ancillas as a a classical system. We're putting dynamics into the ancillas. We're putting, in some sense, classical dynamics into the ancillas, which maybe hasn't been looked at before. But, ultimately, when the dust settles, and when you measure the ancillas, you have the measurement-induced phase transition, which is being revealed, right? So.